Hello folks. Today we are going to learn about a way of thinking that helps to break down a problem into simple steps. This way of thinking is termed as computational thinking. Let's first find out the learning outcome of this video. That is, in this video, you will learn about what is computational thinking, what is the process of computational thinking, why is computational thinking required, stages of computational thinking, what are algorithms, writing algorithms using examples, what is a flowchart, examples of flowcharts, which are the symbols that we use to write in a flowchart, the difference between algorithm and a flowchart, and creating flowcharts with examples. Let's begin by understanding what is computational thinking. Computers can be used to help us solve problems. However, before a problem can be tackled, the problem itself and the ways in which it could be solved need to be understood. Computational thinking allows us to take a complex problem, understand what the problem is, and develop possible solutions. We can then present these solutions in a way that a computer, a human, or both can understand. Process of computational thinking. Computational thinking is the process of breaking down a complex problem into simpler steps, understanding what the problem is, and developing possible solutions. This process involves 4 major stages of thinking and breaking down a complex idea to make it simpler and understandable by a human or a computer. We will share about the 4 stages in detail shortly in this video. Why do we require computational thinking? When students develop computational skills, they are able to articulate a problem and think logically. It helps them to break down the issues at hand and predict what may happen in the future. It helps them to explore cause and effect and analyze how their actions or the actions of others impact the given situation. These skills instilled by computational thinking can have powerful impact on students and how they manage their relationships with those around them. Apart from this, the following are the reasons why computational thinking is required. It builds confidence. It builds analytical skills. It improves the problem-solving skills as well. It enhances logical thinking, and it generates future opportunities in various fields of science and computers for students. Computational thinking helps students develop skills that are attractive for future employment opportunities. Computer science is the fastest growing job market, and students with skills in coding are highly sought after job applicants. While the hard tech skills are very important, it is the softer skills of reasoning and problem solving that are best when learned at an early age. Before we learn about the stages of computational thinking, let's solve a riddle together using this type of thinking. Let's listen to the riddle involves analyzing each scenario. When 2 wildebeests cross, or 2 lions cross, or one of each animal does. If we use computational thinking to solve a riddle like this, we will be able to draw out all possible scenarios and solutions leading to those. Now let's go through the stages of computational thinking. There are 4 key stages or key skills used in computational thinking, and they are: Stage 1. Decomposition. This is the stage of breaking down a complex problem or system into smaller, more manageable parts. Stage 2. Pattern recognition. This is the stage in which we look for similarities among and within problems. Stage 3. Abstraction. In this stage, we focus on important information only, ignoring all irrelevant details. Stage 4. Algorithm. In this stage, we develop a step-by-step solution to the problem or the rules to follow to solve the problem. Each stage is as important as the others. They are like legs on a table. If one leg is missing, the table will probably collapse. Correctly applying all 4 techniques will help when programming a computer and finding a solution. Let's understand each of these 4 stages of computational thinking. Step 1. Decomposition. Decomposition is one of the 4 cornerstones of computational thinking. It involves breaking down a complex problem or system into smaller parts that are more manageable and easier to understand. The smaller parts can then be examined and solved or designed individually as they are simpler to work with. If a problem is not decomposed, it is much harder to solve. Dealing with many different stages all at once is much more difficult than breaking a problem down into a number of smaller problems and solving each one at a time. Breaking the problem down into smaller parts means that each smaller problem can be examined in more detail. Similarly, trying to understand how a complex system works is easier using decomposition. For example, understanding how a bicycle works is more straightforward if the whole bike is separated into smaller parts and each part is examined to see how it works in more detail. Another example of decomposition in everyday life is brushing your teeth. To decompose the problem of how to brush your teeth, we would need to consider which toothbrush to use, how long to brush for, how hard to press on our teeth, and what toothpaste to use. Step 2. Pattern recognition. When we decompose a complex problem, we often find patterns among the smaller problems we create. The patterns are similarities or characteristics that some of the problems share. Pattern recognition is one of the 4 cornerstones of computational thinking. It involves finding the similarities or patterns among small, decomposed problems that can help us solve more complex problems efficiently. Let's first understand what are patterns. Let's take an example that we want to draw a series of cats. All cats share common characteristics. Among other things, they all have eyes, tails, and fur. They also like to eat fish and make particular sounds. Because we know that all cats have eyes, tails, and fur, we can make a good attempt at drawing a cat, simply by including these common characteristics. In computational thinking, these characteristics are known as patterns. Once we know how to describe one cat, we can describe the others, simply by following this pattern. The only things that are different are the specifics. One cat may have green eyes, a long tail, and a black fur. Another cat may have yellow eyes, a short tail, and a striped fur. If we want to draw a number of cats, finding a pattern to describe cats in general, example that they all have eyes, tails, and fur, makes this task quicker and easier. We know that all cats follow this pattern, so we do not have to stop each time we start to draw a new cat to work this out. From the patterns we know cats follow, we can quickly draw several cats. Why are patterns important? And what happens when we don't look for patterns? Finding patterns is extremely important. Patterns make our tasks simpler. Problems are easier to solve when they share patterns. The more patterns we can find, the easier and quicker our overall task of problem solving will be. Suppose we hadn't looked for patterns in cats, each time we wanted to draw a cat, we would have to stop and work out what a cat looked like. This would take longer for us to solve this cat drawing task. Step 3. Abstraction. Abstraction is the process of filtering out or ignoring the characteristics of patterns that we don't need in order to concentrate on those that we do. It is also the filtering out of specific details. From this, we create a representation or an idea of what we are trying to solve. In pattern recognition, we looked at the problem of having to draw a series of cats. We noted that all cats have general characteristics, which are common to all cats. Example, eyes, tail, fur, a liking for fish, and the ability to make particular sounds. In addition, each cat has specific characteristics such as a black fur, a long tail, green eyes, a love for salmon, and a loud particular sound. These details are known as specifics. In order to draw a basic cat, we do need to know that it has a tail, fur, and eyes. These characteristics are relevant. We do not need to know what sound a cat makes or whether it likes fish or not. These characteristics are irrelevant and can be filtered out. We do need to know that a cat has a tail, fur, and eyes, but we do not need to know what size or color these are. These specifics can be filtered out. Why is abstraction important? Abstraction allows us to create a general idea of what the problem is and how to solve it. The process instructs us to remove all specific detail and any patterns that will not help us to solve our problem. This helps us form our idea of the problem. This idea is known as a model. If we do not abstract, we may end up with the wrong solutions to the problems we are trying to solve. With our cat example, if we didn't abstract, we might think that all cats have long tails and short fur. Having abstracted, we know that although cats have tails and fur, not all tails are long and not all fur is short. In this case, abstraction has helped us to form a clearer model of a cat. Step 4. Algorithm. Algorithms are one of the 4 cornerstones of computational thinking. An algorithm is a plan, a set of step-by-step instructions to solve a problem. If you can tie shoelaces, make a cup of tea, get dressed, or prepare a meal, then you already know how to follow an algorithm. In an algorithm, each instruction is identified and the order in which they should be carried out is planned. Algorithms are often used as a starting point for creating a computer program, and they are sometimes written as a flowchart or in pseudocode. If we want to tell a computer to do something, we have to write a computer program that will tell the computer step by step exactly what we want it to do and how we want it to do it. This step-by-step program will need planning, and to do this, we use an algorithm. Computers are only as good as the algorithms they are given. If you give a computer a poor algorithm, you will get a poor result. And in case you give a good algorithm, your result will be better. Algorithms are used for many different things, including calculations, data processing, and automation. The order of planning out how a problem will be broken into smaller parts is done first. This order can be represented as an algorithm. An algorithm must be clear. It must have a starting point, a finishing point, and a set of clear instructions in between. Algorithms can be represented using flowcharts. Flowcharts normally use standard symbols to represent the different instructions. We will share these symbols in this video with you. There are few real rules about the level of detail needed in a flowchart. Sometimes, flowcharts are broken down into many steps to provide a lot of detail about exactly what is happening. And sometimes, they are simplified so that a number of steps occur in just one step. A simple program could be created to ask someone their name and age and to make a comment based on these. This program, represented as a flowchart, would look like: Start. Output: what is your name? The input will be the user inputs their name. Store user's input in the name variable. Output: hello with the name. Output: how old are you? Input: user inputs their age. Store user's age in age variable. Is age greater than or equal to 70? If yes, the output will be: you are aged to perfection. If no, then the output will be: you are a spring chicken. After both scenarios, stop. Computational thinking in practice. If we have a complex problem at hand, here's how computational thinking enables us to deal with it using the 4 stages. This process of thinking involves taking that complex problem and breaking it down into a series of small, more manageable problems. That is the decomposition phase. Each of these problems can then be looked at individually, considering how similar problems have been solved previously. That is the pattern recognition phase. And focusing only on the important details while ignoring irrelevant information. That is abstraction phase. Simple steps or rules to solve each of the smaller problems can be designed. That is the algorithm stage. Finally, these simple steps or rules are used to program a computer to help solve the complex problem in the best way. Let's take an example. If you agree to meet your friends somewhere you have never been before, you would probably plan your route before you step out of your house. You might consider the routes available and which route is best. This might be the route that is the shortest, the quickest, or the one which goes past your favorite shop on the way. You would then follow the step-by-step directions to get there. In this case, the planning part is like computational thinking, and the following directions is like programming. Being able to turn a complex problem into one we can easily understand is a skill that is extremely useful. In fact, it is a skill you already have and probably use every day. For example, it might be that you need to decide what to do with your group of friends. If all of you like different things, you would need to decide what you could do, where you could go, who wants to do what you have previously done that has been a success in the past, how much money you have and the cost of any of the options, what the weather will be like, and how much time you have. From this information, you and your friends could decide more easily where to go and what to do, in order to keep most of your friends happy. You could also use a computer to help you to collect and analyze the data to devise the best solution to the problem, both now and if it arose in the future again. Did you know that Seymour Papert was the first person who gave this type of thinking the name of computational thinking? Well, yes, he mentioned that computational thinking can be used to algorithmically solve complicated problems of scale. The first children's toys with built-in computation were created in Seymour Papert's laboratory in the 1960s. Let's now understand about algorithms. What are algorithms? Algorithms are a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. Algorithms are also a specific procedure for solving a well-defined computational problem. It requires an understanding of the alternatives available for solving a computational problem, including the hardware, networking, programming language, and performance constraints that accompany any particular solution. Let's try and write the algorithms using an example. Let's take an example of making tea. If we have to make tea, there are certain steps involved. Looking at the picture, you will be able to gauge the steps involved in making tea. Let's write these steps involved in making tea. Step 1. Start. Step 2. Put milk in the kettle. Step 3. Add tea leaves and sugar in the milk. Step 4. Heat the kettle and allow it to boil. Step 5. Filter the tea in cups and serve hot. Step 6. Stop. Did you know that the world's first algorithm was written in the year 1815 by Ada Lovelace? Yes, that's true. Now let's understand about flowcharts. But before we begin, first let's find out what is a flowchart. A flowchart is a type of diagram that represents a workflow or a process. A flowchart can also be defined as a diagrammatic representation of an algorithm. Flowcharts are widely used in multiple fields to document, study, plan, improve, and communicate often complex processes in a clear, easy to understand diagram. Flowcharts use rectangles, ovals, diamonds, and potentially numerous other shapes to define the type of step, along with connecting arrows to define the flow and sequence. They can range from simple hand-drawn charts to comprehensive computer-drawn diagrams depicting multiple steps and routes. An example of a flowchart is shown here. Looking at the present times, the Government of India prepared a flowchart or a course of action for people so that they know which steps to follow if they feel unwell. The image gives us a process-oriented approach that helps the citizens to know what they need to do in case they feel symptomatic. Another example of a flowchart is of an alarm ringing in the morning. This flowchart shows the steps to follow once the alarm clock rings in the morning. You can either snooze it and the process repeats, or you end it and wake up. As you can see, a flowchart gives steps for all possible scenarios. Symbols which are used in writing flowcharts are given here. Start or end symbol. This indicates the start and the end of the flowchart, and its function is to terminate the flowchart. Arrows. The arrows are a connector that represent the relationship between the shape and its flow direction. Parallelogram. This represents the input or the output of the program. Rectangle. A rectangle represents a process. A diamond indicates a decision. Difference between algorithm and a flowchart are as follows. Algorithm is a step-by-step procedure to solve the problem. Flowchart is a diagram created by different shapes to show the flow of data. Algorithms are complex to understand. Flowchart is easy to understand. In algorithm, plain text is used. In a flowchart, symbols and shapes are used. Algorithm is easy to debug. Flowchart is hard to debug. Algorithms are difficult to construct. A flowchart is simple to construct. Algorithms do not follow any rules. Flowchart follows rules to be constructed. Did you know who developed the first flowcharts? They were developed by Hermann Goldstine and John Newman in the 1940s. Some frequently asked questions and their answers are given below. Question 1. Are all the stages part of the computational thinking process each time? Answer. Yes. All 4 stages of decomposition, pattern recognition, abstraction, and algorithms are important each time we solve a problem using computational thinking. Question 2. When writing an algorithm, is the order of instructions important? Answer: yes, the order of instructions is very important. Question 3. In a flowchart, how are symbols connected? Answer: symbols are connected using arrows and lines in a flowchart. Question 4. What does computational thinking involve? A. Thinking like a computer. B. Breaking a complex problem down into simple steps. C. Learning how to program. D. Making the problem complex. Answer: option B. Breaking complex problems down into simple steps. This is what computational thinking is all about. Question 5. Which of the following is an example of thinking computationally? A. Planning out your route when going to meet a friend. B. When going to meet a friend, wandering around until you find them. C. When going to meet a friend, asking a parent to plan your route for you. Answer: option A. Planning out your route when going to meet a friend is an example of thinking computationally. Assignment: give the algorithm and flowchart representation of how traffic lights work and the steps to take while we are on a traffic light.